Transient analysis using Laplace transforms. So let's start. Okay. Learn outcome 4. Use Laplace transforms to model transient response of RC, RL, and RLC circuits. So, what Laplace transforms are a mathematical method similar to calculus. There's an alternative method to solving differential equations. So instead of solving differential equations using calculus, Laplace transforms is a method that allows you to solve them through algebra and transfer back. A bit clearer later. In electrical engineering, it's often necessary to analyse the response of a circuit during a transient period. For instance, and most of these you'll be familiar with, the charging of a capacitor, switch on, switch off, which we've already had a look at a little bit in the science module in the first year. Current transient in an inductor circuit at switch on, switch off, and the response of RLC circuits to step and ramp inputs. And then if you was to get involved in control engineering, there's further examples there in terms of looking at how proportional, integral and derivative controllers work, for instance, which is similar to the response you get to a step input for an RLC circuit. Okay. So this so as the underlying theory around transfer functions for process control. So, in using Laplace transforms, you transfer a differential equation solution from one involving integration to one that involves a simpler algebraic manipulation. That's if you're good at algebra. But all maths requires you to be good at algebra. So, what this process involves is transferring the circuit that you have from a normal time domain into a new, what's called S domain, the Laplace transform. Then you manipulate the Laplace equation, the Laplace transform, algebraically, so that it looks like one of the standard transforms in the table, and then once you've got it looking like that, you can transfer it back to the time domain. That's found in the inverse Laplace transform. So similar to in calculus, differentiation and integration are opposites of each other. If you differentiate the equation, then you integrate it, you end up back where you started. This is the same thing. You transfer to the S domain, do your algebraic manipulation, until you're able to transfer using the table back to the time domain. Alright, so for some circuits, step 2 will involve the use of partial fraction, perfect square techniques, and these will be revised and taught within these sessions. Okay, so we've not done anything essentially with perfect square, so we'll be teaching that in the sessions. Right. What is a Laplace transform? So the Laplace transform, f of s of a function f of t, so S domain is the Laplace transform. That one's in the S domain, and it is of a function in the time domain. And it's defined as f of s, being the definite integral between 0 and infinity, e to the minus st times the function with respect to time. Okay, so that's how you find the Laplace transform of a particular function. You take that function and you find that integral of it. for a function where there's a constant multiplier, rather like we do with the normal integrals, we can take that constant multiplier outside of the integral, multiply the result by that constant multiplier. For functions that are summed, so we've got if of t, a function, plus bg of t, another function, we simply find the two parts to that separately and add them together. Okay. So it's the process of finding the Laplace transform for a particular function. We're not going to do too much of for this module. We'll not spend a long time determining Laplace transforms of functions, because the key interest is how to use the transforms to solve electrical problems. But it's worthwhile just looking at a couple that are already in our table that we're going to be using, so we can see how they end up being derived. So if we take the Laplace transform for the constant 1, yeah, we've got to find the S-domain function. We have to integrate e to the minus st times 1. What is the integral of e to the minus st? Anyone remember? Anyone still got their laminated integral tables? Yep. That's minus 1 over s. Yeah, that's how you write it. Okay. E to the minus st yeah, but we're doing a definite integral, aren't we? Yeah. And what's the integral of? Oh, simply we've got a constant multiplier here, don't we? 1. So the 1's come outside, so we can ignore it, because that's 1. It's come outside, and that's just 1. So that's minus 1 over s e to the minus st. Yeah. Plus c, we can ignore that because we're finding a definite integral, can't we? So it's going to be that between 0 and just in the yeah, that minus we can probably better write that as e to the minus st over s and that got a minus on that minus there. Yeah, between 0 and infinity. So 16 points. We can take minus 1 over s outside a set of brackets, and then we want the value of that function. We want e to the minus s times infinity minus e to the power of 0. So that's the value of what's inside there when put infinite, take away the value of the lower bracket. So upper bound, lower bracket. Yeah? That's minus 1 over s times e to the minus s times infinity. The value of that is e to the o is equal to how does the e to the minus graph go as you approach 0? It's as the number here gets bigger and bigger, or a bigger negative number, what happens to the graph? You can't do infinity on your calculator, right? But if you no, you can't. You ain't going to be asked to do this, Tom. Oh. No. Why am I teaching it? I'm teaching it to show you where the Laplace transforms in the table come from. Yeah, so we're going to just do a couple of basic ones just to see where they come from. I'm not going to ask you to use the transforms in the exam, all right? Trust me. Y equals e raised to the minus x. Yeah. So where does x tend toward? Where does y tend towards as x gets bigger and bigger? So e to the power of infinity must be. Are you all happy with that? Yeah. Okay. So we've got 0 minus 1 in there. So that bit in the brackets is minus 1. So the answer must be 1 over s. Yeah. So as you'll see later, step voltage, if this is volts, 5 volts in a time domain, this be a t along here, will equal 5 over s. If we had 5 instead of 1, the constant multiplier outside would be 5. transform into 5 over s. Now, there comes a problem in our writing. 5s and s's look the same. And as much as I try not to get a 5 in any of my questions, there always seems to be one appear from somewhere. So you're going to have to be careful how you write your 5s and how you write your s's, so you can distinguish between the two. I tend to write the s smaller, is what I tend to do, a little bit like not a subscript, but write it smaller than the numbers, so you don't get muddled up between a 5 and an s. Alright? So a constant of 1 turns into in the time domain, turns into a Laplace transform of 1 over s. Like I've said, I won't be expecting you to find a Laplace transform in the exam. If I don't show you where the ones in the tables come from, that's kind of a where do they come from thing. So it's like, some people will think, well, I don't understand that because I don't see where the 1 over s comes from, so I'm kind of shelf. I'm not going to do them all, just doing a couple to understand where they come from. And I won't be asking you to do that in the exam. So, like I said, if there's a constant involved, k, we follow that process through, we'd have because we're going to use we know that if when k equals 1, f of s is equal to 1 over s. By constant multiplier rule, which is what I've already told you. The Laplace transform is equal to k times 1 over s, which is equal to k over s. So it just shows where that comes from. And you're going to be using that transform start from next week to express a step voltage. If you go on to your next page, you'll see that step, or DC, i.e. a function that is a constant a, turns into a function in the s domain of a over s. That table covers all the ones that we use, and actually one I probably won't use, which is the damped cosine one. Okay, but anyway, you'll be given nothing to do that isn't on that table, and that table will be on the back of the exam paper as per other formulae that you may need. Okay, so a ramp input, so input where the voltage is increasing over time, is a over s squared, because we've got a constant multiple function of time, exponential decay. So if we've got this exponential function, it looks like that, the s domain, and so on. So what we're going to be doing eventually is trying to manipulate an equation in the s domain so it looks like one of this side here, and then we can transfer it back to the function in the time domain. And all of that will become clearer as we do examples. Furthermore, when you want to transfer your electrical circuit to the S domain, these are the components. So a resistor of a certain number of ohms just becomes R. Notice, units disappear in the S domain. An inductor, L, is L times S. And a capacitor F is 1 over CS. It is not farads or henries and ohms. The units disappear in the S domain. Okay. So, transferring the impedance, circuit impedance components to the S domain. So the first part of the process that we're going to be working on is to be able to express the circuit in the S domain and just manipulate it a little bit to tidy up and make it what we need before we add the voltage. Generally what we're going to be doing is looking to produce an expression in the time domain for the current in the circuit. Possibly a voltage, but in the main, what's the expression for current? Alright, so we'll consider a simple RL circuit. In the time domain, Z in the time domain is equal to what? Total impedance. Yep. Yeah, and XL is equal to XL is equal to 2 pi FL or omega L. Yeah. And in this situation, we're in a calculus related environment. Our frequency will be in omega form and our calculators will be in radians. Alright? So we can actually say that it is R plus omega L J ohms. Which in this case is 10 plus 2 omega. From the transforms table, RS is equal to R and LS is equal to L times X. Yeah, so what we're saying is the resistor in the S is just equal to whatever the value of R is. The inductor in the S domain is equal to L times S. Alright. It's S is a new domain. Yeah. It's called the frequency domain, but we don't have to worry too much. Sorry, go on. No, it just stays as S all the time. Yeah, you're going to have to live with me for a minute, and when we actually start the proper examples next week, you'll see how it all works. Alright? For the moment, it's not given a number. Usually you assume it's not 0 for reasons of getting errors on your calculator. Alright? But Other than that, I've not. We won't be giving it a value. Yeah. What we're aiming to do, eventually, when we've got an expression for the circuit, including the voltage, we're trying to turn it into a current. So we use Ohm's law. We then want to manipulate the expression we've got so that it looks like one of these. Because then we can transfer it back to an expression in the time domain. But that won't become clearer until next week. All right? So we can now, if we take that, Z in the S domain is equal to R plus L times S, which in this case is 10 plus 2S. No units. Right. Yeah. Go on. Yeah. So his no S goes with R, but that's L2 in the circuit we've got, and that's times S. Yeah. All right. Everybody happy with that? Can we move on? So if we look for a simple RC circuit, we'd have Z in the time domain is equal to R plus sorry. Yeah. I see, yes. That's all right. How I've got it written in my notes, I'll put the minus there. I've got a minus in front of the 1. That's how you like it, yeah? All right. I'm going to argue with you there for a minute, right? I'm going to put that as plus in there. That's how I got it written in my notes. Okay? Because in terms of we're not really interested in that. So it becomes on the table. It's not a negative. It's not a minus 2f. Okay, the minus sign is only there because of the j term to give the negative angle instead of positive one. But in the S domain, that don't matter. Alright, so that's why I've written it like that. From the table, R of S is equal to R. C of S is equal to 1 over C times S. And it's not the value of the capacitor that's equal to minus 2. It's at minus J. But the negative sign goes, which we aren't interested in here. Therefore, Z of S for an RC circuit is R plus 1 over CS, which in this case, for this circuit, is equal to 10 plus 1 over 2S. That's not a Z total, that's Z twice lowercase, that's Z in the time domain. Yeah, Z in the estimate. Right. There is an expression for the total. This is an expression for total impedance in time domain. I'll write it. Yeah, because for a series circuit of resistance is the impedance. It's the impedance of the capacitor. Yeah, everyone agree with that? Yeah. And this one is the total impedance. In the S. Alright? Yeah. So they're two fairly simple series circuits, which we will have a look at. Okay. Also, what we want to consider is how we deal with some other circuit configurations. So we've got a resistor of 5 ohms in parallel with an inductor of 0.2 henries. How could we write an expression in the impedance in time domain? Z lowercase t is equal to. We need to write it all in one go. We can't do it separate. We've only got a parallel circuit anyway. So we'd use product over sum, yeah? So we'd have R times omega L, don't worry about the J, okay, over R plus omega L. Yep, everyone agree with that? So impedance is going to be R times LS over R plus LS. Taking our values from our circuit, that's 5 times 10s over 5 plus 10s. Correct. How much of that? 0.2. Now what I have? Yeah. Equals 10s over 5 plus. No, you can't add them together like that. It's not 5s plus 0.2s, so you can't add them together. Has to stay like that. 1. This board is doing my head in. So it's s over 5 plus 0.2s. Alright? Because you can only add those two terms together if they're both multiplied by s. You've got 0.2s there. Okay, we never give s a number, but it's an algebra because we can do 5 times 0.2 is equal to 1. Yeah? Because that dot in there means times, doesn't it? Yeah. Okay, so we'd be able to add the voltage to that as it stands. Okay. Board's still not right. I will consider an R and C in parallel. Let's go straight for the impedance in the S domain. Well, for the resistor, it's just R, isn't it? And it's times 1 over CS divided by R plus 1 over CS. Then we can put our numbers in. 10 plus 1 over 4s 10 times 10 plus 1 over 4s. Alright. So we can write that top bit as 10 over 4s. No. The 10 is divided not just by 4, but by s as well. Can't do that. No. How could we manipulate that? Yeah. But explain how you say that. Yeah. Okay. Yeah. Let me try and explain it, how I see it. Yeah. Do you all agree we could write that bottom line as a fraction over 1? Yeah? Now how do we divide one fraction by another fraction? Sorry? Yeah, we turn the denominator fraction upside down and multiply. So like this. 10 over 4s times 1 over 10 plus 1 over 4s. Yep. Turn that bottom fraction upside down. Yep. That multiplication gives us, on the top line, 10. And on the bottom line, 40s plus, yeah, I'm going to write it out, because that's 4s times 1 over 4s. 4s over 4s, just so people can see where it comes from. Yeah. Happy with that? Equals 10 over 40s plus 1. 4s divided by 4s is 1. Can we do anything else with that? What we usually want, okay, is we want s without a multiplier. So how can we get s without a multiplier? Yeah. So 10 over 40 is? And 1 over 40 is? All right. Okay. Everyone happy with that? Yeah. So that with that particular one, there's a need for some manipulation of the total impedance expression into a more simpler form before we use it to determine a current. This is going to be doing start next week. Okay. Now, RLC series circuit. So how would I write an expression for Z in the S domain for this? Want to know in terms of RL and C for the minute? Can we do what, Lewis? Yeah, you can if you want. If you Z in the time domain is XL yeah. What I don't want is that minus sign to go and confuse you, because it isn't minus 1 over CS, yeah? So I just want, I want to be careful with that. So in the S domain, it is R plus LS plus 1 over CS. Yeah. In this case, it is 3 plus 1.2 S plus 1 over 0.5 S. Right, here we need to have all of the left-hand side, all of the right-hand side, it should be, all of that side as a single fraction with a common denominator. Yep. So how do we get a common denominator here? How could I better write that so that, how could I get that fraction so that it was just S on itself? Divide it by 2. How can I make that S on the bottom just S on itself? Take that, just that on its own, multiply it by 2. Yeah? I'll still be equal to that then, so I can write that as 3 plus 1.2s plus 2 over s. And do you all agree that I can write these as fractions over 1, just to see where it comes from? No, it isn't. What you're doing is you're seeing straight away that it's 2 over s. I'm saying where that comes from, 2 over s, is multiplying the top and bottom by 2. All right? Yeah. You see things very quickly without doing the little bits in between. I'm trying to show the class where that comes from. All right? So constants we can write in fraction form over 1. Now, how do we get a common denominator here? If we want a common denominator from 3 separate denominators, what can we do? Multiply them all together. Yeah? So, 2s times 1 is s. Yeah? So, we can say we want a common denominator of s. What have I done to this denominator to make it equal to s? What have I done? What do I do to that denominator to make it equal to s? Multiply by s. So if I multiply the bottom by s, I've got to multiply the top by s. Here, yeah, we've got multiplying the bottom by s to get the common denominator. So we've got to multiply the top by s. And that one is just a plus 2, because it's already got the denominator s. Okay? Happy? All right? So, on your own, have a go at that one. Right. All done or not? No. So, Can we go straight for the impedance in the S domain this time, Lewis? Yeah? Jasmine, what are the values? How you done them? And for these, that probably is, in most cases, better to write it like that than times 10 to the power of notation. Yeah. Next. So can I make that S on its own? Yeah. So it becomes 8 plus 0.5 S plus 500 over S. Yeah. And now we can do our common denominator thing. It's going to be over S, and that's going to be 8S plus 0.5 S squared plus 500. Everybody get that? Yeah. Have a look at some solutions, haven't we? You got them right. See if everybody agree. Right. Question 1. Expression in the S domain. Go straight in with the numbers, should we? What you got then, Lewis? Yeah. What you done with it after that? Sorry? What did we do before? Sorry? What you divided through by what? Yeah. An easiest way to say it is divide by 0.6. Yeah. All right. I'll just shout that. How do I turn that into just S? If I divide by 0.6, I've got it now. So I've got to. You can do, but when we do the bit next week, you'll need it with S on its own. Otherwise, the expression, once we introduce, because what we're going to be doing next week is looking for an expression for I in the S domain, and it's going to be equal VS over Z. And if that expression's too complex, then that expression's going to get muddled. All right? So aiming for the denominator have an s on its own. So we divide through by 0.6. That should give us, what did that give us on the bottom? 20 plus s. And on the top, all right? Everyone agree with that? Why you need it like that, Seppi, will become more clear when we start doing that bit next week. All right? Yeah. Second one. Right. Second one. ZS is equal to? Yeah. Next bit. Tidying up. On the top. We did, didn't we? We wrote it as yeah. And then, because that denominator can be written as a fraction over 1, we can say it is equal to 8 over 0.02 s times 1 over 8 plus 1 over 0.02 s. And doing that multiplication gives us 8 over 4. Follow that? Yeah. Follow it, Dom? Eight over 0.16. Everyone follow that? Yeah. Chris? I don't. Right. Third one. Z in the S domain is Jasmine. Didn't you? Oh, okay. Ben then. Yeah. And eventually you'll do that many that you're going to write that first time anyway, I think. That bit at the top there. Like that. Wait a minute. So you've multiplied half of it now. Yeah, but you can't write that now because you got that there. That's only 0.016 over 0.016s once you've done this multiplication, isn't it? Yeah. So the answer. Do you see what I mean? Yeah. So that's 25. Oh, what? 25 of a 0.4s plus 1, and then you divide by 0.4. Just put that on there to get 62.5 over s plus 2.5. Everyone agree with that who got that far? Yeah? Okay. So that is expressing your total impedance of a circuit in the S domain and a little bit of a manipulation to get it in a form ready to turn into an expression for a current using Ohm's law, or an expression for a voltage using Ohm's law in some cases. All right, which will be the subject beginning of next week's lesson. All right.